So in this video, we're looking at solving linear inequalities. So since we're looking at inequalities, let's do a rundown real quick of the 4 different symbols we could see. We have the less than symbol, the less than or equal to symbol, and then we have greater than or equal to. So if the inequality symbol has a little bar underneath, that just indicates that our variable could be equal to the value on the other side. So we are looking at linear inequalities. So solving linear inequalities is essentially the same exact way as solving linear equations. One thing to keep in mind when we're solving inequalities is what happens if we multiply or divide by a negative. So just remember, if we multiply or divide by a negative, then our inequality symbol gets flipped. So let me show you an example real quick. Let's say I have negative 2x is less than 6. From solving linear equations, we know to get x all by itself, we need to divide by the value that's being multiplied to x. So we would divide both sides by negative 2. Negative 2 divided by negative 2 is positive 1, so I have positive 1x, which is what we wanted. And since we divided by a negative, that flips my inequality symbol the other way. So instead of less than, we now have greater than, and 6 divided by negative 2 is negative 3. So we solved our first linear inequality. Typically, we're either going to want to display our solution either on a number line or in interval notation. So this is what we call algebraic notation. And on a number line, we can see that we have greater than negative 3. So I'm going to go ahead and here's 0, and negative 3 would be to the left of that. Since it's strictly greater than and we know it can't be equal to negative 3, on a number line we would put an open circle to show we're starting at negative 3, but negative 3 is not actually part of my solution. And greater than, we may know that the values greater than negative 3 on a number line will be to the right of it, or there is a little shortcut. If I draw a line in the inequality symbol, it now becomes an arrow showing me which direction to shade, so I'll be shading to the right. So there's the number line representation. And then we can also write it in interval notation. Each piece that's shaded will convey to one interval. So I only have one piece that's shaded, so I will have one interval. So I'm going to start at negative 3, and this will go all the way. There's no restriction, so this goes all the way up to infinity. Neither are included, so I get parentheses. So there we go. Those 3 representations for the solution of this linear inequality. So let's do one more regular inequality, beef it up a little bit. Let's say I have negative 3x plus 7 is less than 2x minus 3. So again, just like with solving linear equations, our goal with the inequalities is to get x's all by themselves and plain numbers on the other side all by themselves. So I do have x's on either side of the inequality. So I'm going to subtract 2x from the right, 2x from the left, and I'll subtract 7 from the left, 7 from the right. So negative 3x minus 2x gives me negative 5x. 7 minus 7 is 0, so that cancels out. Bring down my inequality symbol. 2x minus 2x is 0, so that cancels out. And negative 3 minus 7 is negative 10. And now to get x all by itself, I see that negative 5 is being multiplied by to x, so I'll divide both sides by negative 5. And since we divided by a negative, like we saw above, that does flip my inequality symbol the other direction. And negative 10 divided by negative 5 is positive 2. So let's just say we want to write this in interval notation. X can be any number greater than 2. So our interval notation would be 2 to infinity with parentheses, since again it can't be equal to. All right, so these are just basic linear inequalities. There are a couple of different types of inequalities. We can have a compound inequality. And so instead of having just 2 sides, we actually have 3 sides. So an example of a compound inequality, say I have -5 less than or equal to 2x plus 9 is less than 3. You see that I do have 3 sides of the inequality. The goal here is still the same. I'm trying to get x all by itself. So focusing on the center here, I'm going to solve this just like a regular equation or inequality. I need to get rid of the 9, so we'll subtract 9, but instead of just left and right, I'll do it from all 3 sides, and then eventually we'll divide by 2. So let's start by subtracting 9, and I'll subtract 9 from all 3 sides. -5 minus 9 is -14, less than or equal to 2x. 9 minus 9 cancels, which is less than 3 minus 9 is -6. And now x is being multiplied by 2, so I'll divide all 3 sides by 2. I get -2 is less than or equal to x, which is less than -3. And so again, the different representations for our solution. Let's go ahead and put a number line on here. So I can see that x is going to be strictly less than -3. So right here, an open circle, and less than, I know that's going to be to the left of -3, so I'll shade to the left of -3. And on the other end of this, we kind of have to read it backwards. This says that x is greater than or equal to -2. So I can come off to the side and write that. That says x is greater than or equal to -2. You kind of got to read it backwards. So since it's equal to on a number line, we'll have a closed parenthesis. And then again, it says greater than, so this would be shaded to the right. The values that are greater than -2 are going to be to the right of -2. Notice here that we have 2 pieces on the number line that are shaded. So I'm going to have 2 intervals if I'm going to write this in interval notation. Everything less than -3, so this would be -infinity to -3, neither included. And we'll use a union to connect my 2 intervals. So the second interval starts at -2, goes up to infinity. This time -2 is included, so we'll use a bracket and a parenthesis for infinity. So there's our compound inequality, our solution written in interval notation. And so the last type of inequality you may run into, generally they're called an and or situation. So you'll be given 2 inequalities, and our goal is, if it's an and problem or an and statement, we're looking for the solutions that satisfy both of the inequalities or make both of the inequalities true. If it's an or statement, then it could be one or the other. So let's look at an example of that real quick. These are the and or problems. So let's say that we're given 2x plus 4 is less than or equal to 5, and 6x plus 1 is greater than 7. Regardless if the situation is and or, you're going to start off by solving both of the inequalities. So we're going to start off doing that, and then we'll look at what would it look like if it was an and situation, what would it look like if it was an or situation. So I'll subtract 4 from both sides. Divide by 2, I get x is less than or equal to 1/2. And for the second, subtract 1. Divide by 6. I get x is greater than 1. So let's look at this on a number line real quick. So here is 0, here's 1/2, and here is 1. So less than or equal to 1/2, I'll have a closed circle on 1/2 and shaded to the left. Greater than 1, I'll have an open circle on 1 and shaded to the right. Now if this were an and problem, so let's say an and problem, what this is looking for, what it comes down to is where the shading overlaps, because if it overlaps, then those solutions will work for both of the inequalities. We can see here that nothing overlaps. These values will only satisfy this inequality, and these values will only satisfy the right inequality, none of the values will satisfy both of the inequalities. So this problem, if it were an and problem, would actually have no solution. Because remember, and is looking for the solutions that will satisfy both of the inequalities. Now, if this were an or problem, so we still have the same setup, we would still solve both of the inequalities, look at the solutions on a number line. So again, 0, 1/2, and 1. Open circle. There we go. Just running through that again. So if this were an or situation, an or statement is looking for what are the solutions that would either satisfy the left inequality or the right inequality. Well, we know that all of these answers will satisfy the first inequality, and all of these answers or solutions will satisfy the second inequality. So all of the values that would satisfy either one ends up being all of the values. So if it were an or situation, we would have -infinity to 1/2 union 1 to infinity, because all of these values will satisfy either that inequality or that inequality.